Flipper Zero Deep Dive. Today, we're exploring a device that has captivated the security community, the Flipper Zero. It promises to be a master key in a world of digital locks, consolidating an entire toolkit of specialized hardware into a single, pocket-sized device. But what makes this instrument so powerful, and what does its existence say about the security of the world around us? Core hardware capabilities. To understand the Flipper's power, we must first look under the hood at its impressive array of built-in tools. This isn't just one instrument. It's a symphony of radio transceivers and physical interfaces designed to interact with the hidden digital landscape. We'll now explore the core hardware that makes this device a universal translator for the signals that surround us every day. What specific hardware is integrated into the Flipper Zero that makes it a multi-tool for pen testing? Think of it as a decathlete of digital signals, engineered to be proficient in many disciplines rather than a master of one. Its architecture brilliantly integrates multiple radio chips and contact-based readers onto a single board, all orchestrated by a low-power microcontroller. This design philosophy means it can speak the language of everything from your garage door to your office access card, acting as a universal remote for the modern world. Let's focus on the sub-GHz transceiver. What class of devices does this allow you to interface with? The sub-GHz transceiver is its long-range ear, listening to the invisible chatter of our simplest devices. This is the realm of garage door openers, wireless weather stations, and many first-generation IoT sensors that shout their status into the void on frequencies like 433 MHz. Because these systems were designed for convenience, not security, they often use simple, unencrypted protocols that this tool can easily record and understand. How does it interact with proximity-based systems like access cards? It essentially becomes a ghost in the machine for those systems, using dedicated antennas for both low-frequency 125 kHz signals, common in older office badges, and high-frequency 13.56 MHz NFC signals used in modern credit cards and transit passes. It can listen to the unique song of a card, remember it, and then sing that same song back to the reader. The device can therefore read, save, and emulate these cards, acting as a digital skeleton key. Beyond radio, what are the GPIO pins for? Those pins are a direct line into the brain of other electronics, a hardware-level chat interface. They allow an examiner to speak the native languages of microchips, such as UART, SPI, or I2C, which are the foundational protocols for communication between components on a circuit board. By connecting to these GPIO pins, the Flipper transforms from a radio tool into a powerful hardware debugging and reverse engineering platform. The encryption paradox. So, we live in a world secured by digital fortresses, where nearly everything from our banking to our messages is wrapped in powerful, complex cryptography. Yet, into this world comes the Flipper, a tool that seems to find cracks in these fortress walls. The fascinating question is not whether the encryption is strong, but whether the doors and windows of the fortress were installed correctly in the first place. Given that most modern communication is protected by strong encryption, what is the practical application of this tool? This tool isn't a battering ram designed to shatter the steel door of modern encryption like EES. It simply doesn't have the computational power for that. Instead, think of it as a clever locksmith who notices the main gate is secure, but the small, forgotten service entrance is only held by a simple latch. Its power lies in exploiting these implementation weaknesses, not in breaking the cryptographic algorithms themselves. If it cannot break modern cryptographic ciphers, Where does its utility in a security context lie? Its true genius is that of a digital archaeologist, uncovering forgotten technologies and design flaws buried within modern systems. It excels as a protocol analysis tool, identifying and interacting with insecure legacy systems that often coexist with newer, encrypted ones. It doesn't need to pick a complex lock if it can find an old, rusty key that still fits a forgotten keyhole. Can you give an example of a legacy protocol that might be vulnerable in a modern environment? Imagine a brand new skyscraper with a state-of-the-art biometric security system at the front door. However, to save on costs, the back door leading to the garage still uses a simple, unencrypted keycard system from the 1990s that was never decommissioned. The flipper is the tool that ignores the formidable front door and simply clones the old keycard, reminding us that a system is only as strong as its most vulnerable, forgotten part. How does the flipper handle systems with rolling codes? A rolling code is like a secret handshake that changes every single time you use it, which makes a simple replay of one handshake useless. The flipper approaches this not by trying to guess the next handshake, but by analyzing the system that generates it, a technique known as implementation analysis. It studies the dance rather than just one move, looking for patterns or weaknesses in the choreographer's design. From a professional development standpoint, what mindset does this tool cultivate? It forces a shift in perspective, teaching a mindset of holistic security analysis. Instead of just admiring the strength of a single cryptographic wall, it encourages you to walk the entire perimeter of the castle, checking for unlocked gates, crumbling foundations, and poorly designed defenses. It proves that in security, the entire system implementation matters far more than the strength of any single component. The modern threat landscape. We're about to confront a startling truth about the world we've built, a world filled with devices that are constantly talking. The question is, how many of them are simply shouting their secrets for anyone to hear? The prevalence of insecure hardware is a foundational issue in our modern technological landscape. How prevalent are insecure, unencrypted devices in the current IoT and industrial landscape? A staggering portion of the Internet of Things operates like a crowded room where conversations are being shouted in the open, with some reports suggesting over 40% of IoT transactions use no encryption at all. This isn't a niche problem. It's a fundamental design choice in a vast number of the smart devices we deploy in our homes, cities, and industries. The digital air around us is thick with unencrypted data, and much of it is broadcast in the clear. What specific categories of devices are most commonly found to have these vulnerabilities? We're talking about a vast ecosystem of devices, from the smart meters on the side of your house to the inventory sensors in a warehouse. In a corporate setting, this includes older building access systems, environmental monitors, and even the controllers for industrial machinery. These devices form a shadow network of vulnerable systems, often overlooked and unprotected, operating right alongside the secure corporate IT network. What are the technical or economic reasons for these persistent vulnerabilities? The answer is a classic engineering triangle of trade-offs: cost, speed, and security. For many manufacturers, especially in the competitive IoT space, getting a product to market quickly and cheaply is the top priority. Implementing robust security is complex and expensive, so it's often treated as a secondary feature rather than a core requirement, leading to a flood of persistently vulnerable devices. Can you detail a basic replay attack against a static code system? Imagine your garage door opener uses a static code, meaning it sends the exact same digital password every single time you press the button. A replay attack is as simple as the flipper recording that password when you transmit it, just like recording a snippet of audio. It can then play back that exact same password later, and the garage door, not knowing any better, will obey the command and open. Hardware expansion and coprocessing. Now we arrive at one of the flipper's most defining features, its capacity for growth. The device isn't a static object, but a platform designed to evolve, thanks to a small but powerful gateway to the outside world. These GPIO pins are the secret to its hardware expandability, allowing it to connect with and control other electronic modules. How do the GPIO headers allow for hardware expansion? These expansion headers are like a universal docking port, allowing you to physically connect other specialized electronic modules directly to the flipper's main processor. This means you can augment its built-in tools, for instance by attaching a more powerful radio for long-range experiments or a GPS module for location-based projects. It transforms the device from a self-contained instrument into the brain of a much larger, custom-built analysis machine. The ESP32 is a popular add-on. What specific processing and network capabilities does it bring? The ESP32 is a processing powerhouse in its own right, a specialist in network communications that brings its own Wi-Fi and Bluetooth capabilities to the table. When paired with the flipper, it acts as a dedicated coprocessor, offloading all the heavy lifting of network analysis from the flipper's more modest main chip. This symbiotic relationship allows the flipper to punch far above its weight, turning it into a formidable Wi-Fi and Bluetooth analysis tool. How can this combination be used to analyze Wi-Fi networks? In a controlled lab setting, this combination could be used to perform a deauthentication attack, which is like telling a person's phone it's no longer welcome on the Wi-Fi network, forcing it to disconnect. It could also create a rogue AP, a fake but legitimate-looking Wi-Fi network, to test whether devices can be tricked into connecting to a malicious access point. These are foundational techniques for testing the security responses of wireless clients. What is the role of specialized firmware like Marauder on these ESP32 boards? If the ESP32 is the network specialist, Marauder is its specialized set of tools, like a surgeon's kit for wireless protocols. It's a specific firmware loaded onto the ESP32 that is purpose-built for Wi-Fi and Bluetooth penetration testing. The flipper then acts as the user interface, a convenient screen and controller for commanding the powerful Marauder toolkit running on the connected board. What is the advantage of using an external CC1101 module? The internal radio is a generalist, but an external CC1101 module is a specialist with a much more sensitive ear. It often provides access to a wider range of frequencies and offers superior reception, allowing it to pick up weaker signal from farther away. This is crucial for analyzing exotic protocols or performing security assessments in environments where signal strength is a limiting factor. The firmware ecosystem. The soul of the flipper is not in its plastic shell or even its circuit boards, but in its software. The firmware is the operating system of the device, and its open source nature has given rise to a vibrant and diverse ecosystem. This software architecture is what ultimately defines what the device is and what it is capable of doing. Why is the firmware architecture so central to the flipper's functionality? The firmware architecture is everything. It's the bridge between your intent and the device's hardware capabilities. It acts as the central nervous system, deciding which tools are available, how they behave, and what features of the hardware are unlocked. The choice of firmware fundamentally changes the device's personality and power. What are the key philosophical and functional differences between the stock firmware and a fork like Extreme? The key difference is philosophy, which translates directly into function. The stock firmware is like a car governed by the manufacturer for maximum safety and legal compliance, ensuring it operates strictly within regulated limits. A community fork like Extreme is the same car with the governor removed by a racing team, designed to push the hardware to its absolute limits for research and performance, with the understanding that the driver is responsible for their own actions. What does it technically mean when a firmware unlocks transmission frequencies? This refers to the software-level restrictions placed on radio transmitters to comply with the laws of different countries, as some frequencies are reserved for licensed operators like emergency services. Unlocking transmission frequencies means removing these software guardrails, allowing the device to transmit on frequencies that may be illegal in a specific region. It's a powerful feature for research, but carries significant legal responsibility. Let's discuss a non-radio vector, the bad USB functionality. How does that work? A bad USB attack is a beautiful and terrifying piece of social engineering translated into hardware. The flipper pretends it's not a storage device, but a simple human interface device, like a keyboard. Once connected, it can begin typing a pre-programmed script of commands at superhuman speed, effectively hijacking the host computer. What is a practical use case for this in a security audit? In a security audit, a tester might use this to check if a company's workstations are properly secured against unauthorized USB devices. They could program a bad USB payload to, for instance, open a command prompt, download a benign file from the internet, and execute it. This would instantly reveal weaknesses in the company's endpoint security policies without causing any real harm. Network traffic analysis. We now enter the realm of digital eavesdropping, where the act of listening is just the first step. The truly fascinating part is the ability to capture encrypted whispers today with the hope of understanding them tomorrow. This introduces the powerful concept of offline analysis, where patience and processing power can unravel secrets long after they were transmitted. Can a flipper be used to capture encrypted network traffic for offline analysis? Yes, and this is a cornerstone of wireless security analysis. The device can be used to create packet captures, or PCAP files, which are the digital equivalent of a high-fidelity audio recording of all the raw data flying through the air. Even if the data is encrypted, the recording itself is perfectly preserved, waiting for a key or a vulnerability to unlock it later. How is a WPA2 protected Wi-Fi network vulnerable to this type of capture? A WPA2 protected network is vulnerable because the authentication process itself can be captured, even without knowing the password. When a new device connects, it performs a cryptographic negotiation with a router called a four-way handshake to prove it knows the secret key. The flipper can silently record this entire handshake from the air without ever needing to connect to the network itself. Why is this captured handshake a critical asset for an offline attack? That captured handshake is the crown jewel for an offline attack because it contains a cryptographic challenge and response that is directly tied to the network's password. The attacker can then take this message authentication code and use powerful computers to try millions of password guesses per second against it in a brute force or dictionary attack. It's like having a single, perfect recording of a lock's tumbler clicking, which you can then study indefinitely to figure out the combination. In an unencrypted open Wi-Fi network, what is the effective difference between HTTP and HTTPS traffic? The difference is as stark as sending a postcard versus a sealed letter in a locked box. On an open Wi-Fi network, sending data over HTTP is like sending a postcard. Any mail carrier, or in this case, anyone on the network, can read the entire message in plain text. Using HTTPS is like using a sealed letter, where the contents are protected by a layer of TLS encryption, even if the envelope itself is being carried through a public space. Even with HTTPS, some metadata leakage occurs. What information is typically exposed? Even inside that sealed HTTPS envelope, there's a tiny window that exposes a crucial piece of information. This is due to a mechanism called server name indication, or SNI, which is sent in clear text before the main encrypted session begins. It's the part of the negotiation that tells the server which website certificate you're requesting, so anyone listening knows the destination domain name you're visiting. What kind of intelligence can be gathered from this metadata alone? An observer can learn a tremendous amount through traffic analysis alone. Even without reading your data, they can see you're communicating with a specific bank's domain, how frequently you connect, and the size of the data packets you're sending and receiving. Over time, this metadata can be used to paint a surprisingly detailed picture of your online behavior, even if the content of that behavior remains a secret. What is the status of technologies designed to mitigate this, like encrypted client hello? Yes, the security community is actively working on a solution called encrypted client hello, or ECH. The goal of ECH is to encrypt the entire first part of the negotiation, including the SNI, effectively making that transparent envelope opaque. When widely adopted, this will be a massive leap forward for privacy, closing one of the last major metadata leaks in TLS. Professional and ethical considerations. We've explored the immense power of this tool, but with that power comes an equally immense responsibility. This isn't just a question of technical skill, but of character and intent. The final and most important topic we must discuss is the ethical framework that must govern the use of such a device. For a security professional, what is the ethical framework for using a tool this powerful? The ethical line is drawn with two clear principles: authorization and intent. A security professional operates like a surgeon who would never perform a procedure without the patient's explicit, informed consent. Every test must be confined to a strict, predefined scope, and the goal must always be to diagnose and help heal vulnerabilities, never to cause harm. What is a creative, non-obvious use case you have seen for this device in a professional context? One of the most brilliant applications I've seen was in the field of accessibility. An engineer used a flipper to reverse engineer the proprietary remote control signals for an older, non-smart adjustable bed. They were then able to build a custom, voice-activated control system for a person with severe mobility issues, giving them a level of independence they hadn't had before. What does the popularity of this open-source hardware signify for the security industry? Its immense popularity signals a fundamental shift in the security landscape, the democratization of hardware tools. For decades, this level of capability was restricted to expensive, specialized equipment, but open-source hardware has shattered that barrier. It represents a grassroots movement, a growing public desire to not just use technology, but to understand, question, and hold accountable the invisible systems that govern our lives. What is the single most important principle this tool teaches about real-world security? The most important lesson it teaches is that security is a process, not a product. No system is ever perfectly secure. It is a dynamic state of continuous verification, adaptation, and humility. This tool is a constant reminder to question assumptions, inspect the obvious, and never underestimate the power of a simple flaw in a complex system.